I'm going to talk about electric circuits, including batteries and currents. I'll assume that you know what charge and electric forces are. If you don't, I would invite you to watch my videos on those topics. Okay? So let me start by defining what an electric circuit is. An electric circuit is a closed path through some medium over which charged objects move. All right, for example, imagine you had a flexible metal wire and you bent it into a circle, so you made both ends touch. Okay? The metal in the wire contains electrons. Imagine that those electrons were moving around the circle. Okay, that would be an example of an electric circuit. Okay, it's a closed path. In this example, it's a circle through some medium, in this case, the metal of the wire, over which charged objects move. For the circular wire example, the charged objects are electrons. Here's another example. Suppose that you had a tube filled with salt water, okay, and you bent it into a circle, just like in the example where I bent a wire into a circle. Okay, so you close both ends, so there was a sealed tube like a hula hoop or a torus, if you know what that is, and so you have salt water inside. Okay, now you might know that salt water is composed of ions. Ions are charged atoms and molecules. All right. If those ions moved in the circle through the salt water, that would be another example of an electric circuit. Okay, the closed path is a circle. The medium is the salt water. The charged objects are the ions. Okay? Now, you might ask, why do charged objects move through electric circuits? Okay, well, remember that charged objects exert electric forces on each other. So if there were electric forces, that would be one way to get charged objects to move, right? Through an electric circuit. That is what electric batteries are used for. Okay, so let me now define what an electric battery is. An electric battery is a device that converts chemical potential energy into electric potential energy. Okay, so yes, there are electric forces that make charged objects move in electric circuits. Okay, those electric forces are associated with electric potential energy. Okay, and batteries can provide that electric potential energy from another type of potential energy called chemical potential energy. Okay, the chemicals inside the battery have a different type of energy that supplies the electric potential energy that leads to the motion of charged objects in an electric circuit. Okay? Let me give you an example now. If you've ever looked under the hood and seen a car battery, you know it looks something like a brick, and you've got these metal little knobs on the top of the car battery. They're referred to as nodes. Okay? And you may have also seen that one side is labeled with a plus and one side is labeled with a minus. Now, I don't recommend you do this. This is actually dangerous. But if you did this, if you connected a piece of metal wire between those two nodes, there would be an electric force in that metal wire that would push the charge carriers through that wire. Okay? You've just created an electric circuit. Okay? In fact, you might do this even when you don't intend to. I heard about a mechanic that laid a monkey wrench between the nodes. And yes, that created an electric circuit, and charge carriers moved through the wrench, and it gets even better. His wedding ring was touching the monkey wrench, and it turned cherry red, so he burned a nice little ring scar on his ring finger. All right. But anyway, so there's an example of an electric circuit. Okay. The battery is providing the electric potential energy, which leads to an electric force that pushes charge carriers through the wire between the nodes. Okay? Now, we can refer to charge in motion by the term electric current. Okay? Let me now type out what electric current is so that there's no misunderstanding. Electric current is charged objects in motion, or the motion of charged objects, the movement of charged objects. All right? So for the example with the wire, if there was electrons moving through the wire, we would say that there's an electric current through the wire. For the salt water, we would, if the ions were moving in the salt water, we would say that that's another example of electric current. All right? Now, let me give you some further details regarding current and batteries. Okay? Okay, so let me give you the units of current. Current is measured in units of amperes or amps. Okay? 1 amp equals 1 coulomb per second. Imagine that you analyzed a section of wire in an electric circuit and you saw 1 coulomb passing by that section every second. Okay, in other words, that amount of charge, 1 coulomb passing by that section every second. We would say that that electric circuit has 1 ampere of current. Okay? So current, 1 amp is the amount of charge that moves through some surface per unit time. All right? The direction of current is with respect to the direction that positive charge carriers would move. Okay? Let me explain this with an example. Give me a minute to make a picture. Suppose that I had a positively charged cube, okay, positively charged object, and a negative negatively charged cube or any negatively charged object. And let's say that I placed a piece of metal between those two charged objects, okay, so that the ends were touching one of the objects. Then can you see that the electrons in the metal would move away from the negatively charged object and they would move to the positively charged object? Remember the way that electric forces work. So the same type of charged objects that are charged with the same type of charge repel each other. Charged objects that are charged with different types of charge attract each other. All right? So electrons would be attracted towards the positively charged object. So they would move from right to left. Okay? Now, however, instead of a metal wire with electrons, suppose that I instead connected those two charged objects by a tube of salt water. Okay? Now, if the positive ions in the salt water would be attracted to the negatively charged object, right? Again, because positively charged objects are attracted to negatively charged objects, all right? So all of that is to say that positive ions would move in a different direction than the electrons, okay? So there's this ambiguity with respect to the direction of current. Can you see that it depends on the type of charge carriers? Okay? To avoid that whole ambiguity, we say that the direction of current is with respect to the direction that positive charge carriers would move. Okay? So even if you had a piece of metal, and even if you had electrons moving to the left, we would still say that the current is to the right. Okay, that's the direction of electric current. Okay, so keep that in mind when we talk about the direction of current. Okay, and I've already emphasized that you can have different types of charge carriers. Okay, you can have negative charge carriers like electrons and positive charge carriers like positive ions. All right. Now, let's mention how batteries are characterized. So I said that batteries supply electric potential energy that leads to the electric forces that move charge carriers in electric circuits, right? A measurement that's proportional to the amount of electric potential energy that the battery supplies is a measurement of what we call voltage. Voltage, the amount of voltage of a battery corresponds to the amount of electric potential energy it provides for circuits. Now, there's a lot more that I could say about voltage. All right, you've probably heard people talk about 10-volt batteries, 12-volt batteries, okay, things like that. So just know for right now that when you hear voltage, that's associated with the amount of electric potential energy. Okay, so obviously if you have a lot of voltage, it means you have a lot of electric potential energy and therefore a lot of electric force, right? So you might guess correctly that a high voltage would lead to a large amount of current. Okay? Now, I would like to make one more comment about current. So we know from the law of conservation of charge that we can't create charge out of thin air, and that we also can't destroy charge. So the amount of charge in the world is the same as it was 1,000 years ago. Okay? Now, because of that, we can't make current out of thin air because we can't make charge out of thin air. Okay? So there's a certain amount of bookkeeping that has to work out. Let me show you what I mean by that. So if I have, let's say, 8 amps of current traveling down this wire. All right? And let's say that there's a fork in the road, so to speak. So let's say that it branches off into 2 pieces. And suppose that I measure the amount of current moving in the top piece, and I measure it to be 6 amps. Okay? Then the amount of current flowing through the bottom piece must be 2 amps. Okay, why? Because the total current in both of those pieces has to add up to the same amount of current I started with. Okay, so 6 plus 2 equals 8. All right? There's an analogy with water. If I have 8 gallons traveling down a pipe that splits into 2 pipes, if 6 gallons go down one of the pipes, then 2 gallons have to go down the other pipe, right? The water has to go somewhere. Okay, so think about that image if that helps. Okay? So this bookkeeping that has to work out allows us to figure out the charge on certain pieces of electric circuits. Okay? So let me do an example of a problem where one might be required to find the current in a piece of a circuit. So suppose that I knew that there was 4 amps in one part of a circuit, and I knew flowing through that part, and I knew that there was 12 amps flowing through another part, and they joined and became just one piece of wire. Then by summing those, I know that that one piece of wire must have 16 amps, because again, from the law of conservation of charge, the currents the bookkeeping has to work out. Okay? So that would be one way you could figure out the current in that one piece, that has to be 16 amps. All right, let me have you try a similar problem now. Suppose I had 100 amps flowing through a piece of wire. So I'm going to write here 100 amps, 100A. And that wire splits into lots of pieces. And I'm going to give you the current through a few pieces, and you have to figure out the current through the rest. So give me a minute to make a picture. All right, so there's lots of branching going on here. So let's say that I'll put a 40 amp next to one of the pieces of wire, and I will put, let's say, a 5 amp label on another piece of the wire, and then 2 amps. Okay, and then I'm going to put a question mark next to a few other pieces of the wire. All right, and what I want you to do is I want you to figure out the amount of current flowing in the pieces of the of this electric circuit that I've labeled with a question mark. All right, so pause the video and see if you can work all those out, please. All right, so I'll go ahead and work it out. So the 100 amps was split into a piece that had 40 amps. So that means that the other piece, there's only two, the other piece has to have 60 amps of current. All right, and then the 40 amps was split into one piece that had 5 amps, so the other piece has to have 35 amps. And then the 60 amps was split into one piece that had 2 amps, so the other piece must have 58 amps. All right?